I think it's time, Dan.
Yeah, maybe maybe people want to make some coffee. Anyway, I guess we can start. All right, so welcome back everyone to the last session of the Australian evening and the European morning sessions of the conference, and we're gonna conclude with a talk by William Mead, who will speak to us about the two-species PACEP.
Okay, thanks, Dan, and yeah, thanks for the opportunity to speak. And yeah, I guess thanks for, if you're in Australia, staying online so long, and if you're in Europe, for getting up so early. Yeah, so this is based on work I've done with Gier and Michael Wheeler as part of my master's thesis. So I may as well just get started. To begin with, I'll just give a general outline of what I'll be talking about today. So firstly, I'll be talking about some known results, single species stochastic models. So I'm going to be talking about exact multi-integral expressions and some asymptotic analysis that follows on from these, giving a bit of a sketch of that. But in general, this is quite well known, and this is about the RSET. Then I'll be talking about a two-species model, which is, I guess, the more novel research we're doing here. I'll be doing this with two different approaches. I'll be talking about a traditional direct sort of approach, and then I'll be alluding to an alternative, more general approach, hoping to, I guess, focusing on exact multi-integral expressions again, and then alluding to how we can deal with asymptotic analysis in the future. But for the most part, I'll just really be talking about this sort of traditional direct approach. So I may as well get started. So to begin with, I'll talk about the asymmetric simple exclusion process, the RSEP. And I think this will probably be revision for a lot of people in the audience. So the RSEP is going to be a stochastic interacting particle system in 1+1 dimensions. So we're going to have one time dimension and one space dimension. So we're going to, with the one spatial dimension, we're going to have particles moving on a 1D lattice. And then they're going to move in time. They can jump to the right at rate p, and they can jump to the left at rate q, but they can only jump if that site is vacant. So this particle here on the left can move to the right and to the left, but these ones can't. And that's the exclusion nature. So this is going to be a Markov chain. So our time evolution in the future is only going to depend on current state. This is going to be a Yang-Baxter integrable system. So this is going to give us a nice sort of toolbox of techniques we can use to come up with some observables for this system. And we're going to mainly be focusing here on the totally asymmetric version, which we can get by setting p equal to 1 and q equal to 0, which in effect means particles can only move to the right, and we're going to expect some sort of drift in time as particles move to the right. And we're going to consider again the continuous time version of the TARSEP, which is a Poisson process. So we're going to have exponential clocks on these movements. And we can consider discrete time as well if you want, but I'll be talking about continuous time. Firstly, we're going to be talking about the infinite lattice Z. So we're going to put n particles on this infinite lattice Z. All these particles are indistinguishable, so we can't tell them apart. We're going to say that the probability of the time evolution, or the probability of, the time evolution of the probability of this system of finding our particles at positions nu at time t, the rate of change of this probability is going to be given by this. And this is a master equation. So rather than go into details, this is basically got n terms here, which describe the number of ways we can jump into the system. And then there's n ways we can jump out of the system. So this says nothing about the particle interactions, and we can encode the particle interactions and describe them by imposing n-1 boundary conditions on this. So the n-1 boundary conditions are going to be only describe two particle interactions, and that's all we need to do to describe the nature, to describe the time evolution of this model, and that's because this is an integrable model. So the main result here, which I'm going to talk about, is the result due to Tracy and Whittam, which says that if we have initial conditions mu and final conditions nu on the lattice Z, that the exact probability of transferring from mu to nu in some time t is going to be given by this multi-integral expression. So rather than go into detail about what this means, we require that this Green's function is going to satisfy the master equation above, the boundary conditions, which I alluded to earlier. And because this is a Green's function, we're going to have some delta function initial condition, which says that at time t equals 0, the system can only be found in its initial conditions. So to unpack this formula a little bit, we're going to have basically n z integrals here. They're all going to surround the origin, complex contour integrals, and then we're going to have a sum here over some permutations, pi. So this is telling you that we're going to be, that Tracy and Whittam have used a coordinate beta ansatz in this work. The only time dependence in this formula is associated here with this exponential. So we've got this exponential of the inverse of z. So that means at the origin, we're going to have this essential singularity, which in practice makes this a little bit more difficult to work with. But anyway, from this expression, we're going to start calculating something called a crossing probability, and I'll define what that means. But to start with, we're going to set our initial conditions mu to be, the ith particle is going to be at lattice site I. So this means that all our particles are initially going to be adjacent to each other. And then we're going to define this crossing probability, Pcross. This is going to be the probability that the positions of all particles are beyond a wall at position S. So here's a diagram of what we can expect here. So we've got a space-time diagram where I've put my positions of 3 particles here. This is their initial positions. And then as time goes on, we're going to expect these particles to drift to the right in time. And then I'm going to put some wall S here. And then I'm only going to count configurations where all particles have crossed this wall. So in practice, to calculate this, we'd start with our Green's function, and then we would be basically be summing over the configurations where all particles have crossed the wall. Yeah, but in practice, what we're really hoping to do here is actually to scale this wall in time, so that then we can sort of expect that this, so it will actually write this wall here as a function of time, so that then as these particles move along, they're sort of going to be moving with the wall. And then we're going to see whether or not they're beyond it or behind it. And we're going to expect to see some sort of fluctuations about there. But obviously, because this is a stochastic model, I've drawn these as straight lines, but really this is a stochastic model. So we're going to expect some sort of random behavior. But this is just giving you the expected macroscopic picture of a drift. So we can, with a bit of work, we can write down this crossing probability as a Fredholm determinant. So basically an infinite size determinant, x and y here are going to be integers. The convergence is taken care of here. And our Fredholm kernel is going to be the sum of n terms here, where I've got these functions phi and psi. And what are these functions? Well, they're going to be defined in terms of contour integrals. So we're going to be adding up the product of n of these. I don't really care too much about what these look like, but they are defined in terms of contour integrals. And basically what we want to do now is sort of deform these contour integrals and then take a limit as time goes to infinity. So with some, I guess some very, this is actually quite a bit of work to show this, but we can deform the contours and do a steepest descent analysis. If we scale k, which was this little subtext here, and we scale k with vt, where v is going to be the expected macroscopic drift velocity of the particle bulk. So vt is going to be our, I guess, lowest order approximation for where the particle bulk will be located. And then we're going to minus away this kappa times t to the 1/3. So we're sort of expecting fluctuations about this mean behavior of order t to the 1/3, and kappa is just going to give us the amplitude of these fluctuations. So this converges uniformly, and we don't really care about what these functions f1 and f2 are, but they need to be there. So with a bit more work, we can actually show that this Fredholm kernel we had earlier, if we make the scaling of k like we discussed earlier, and then we also scale the number of particles in time as vt, as t goes to infinity, this is going to go asymptotically like this integral here over kappa of these airy functions. And you may recognize this as the airy kernel over these functions xi1 and xi2. So this is this will probably be familiar to some people in the audience, but yeah, we can show that these two things are going to go asymptotically to the same limit. And basically what we're doing now is in the limit t goes to infinity, we're replacing this sum with an integral. So this airy kernel satisfies this condition where if we take a determinant of 1 minus this airy kernel, this is going to give us the Tracy-Widom distribution for the GUE. So this GUE consists of n by n Hermitian matrices with randomly distributed entries. And if we take the limit of the matrix size to infinity, we end up with this Tracy-Widom distribution, which is going to be the largest eigenvalue of that matrix. So if we put all this together with a lot more work, Johansson has shown that if in the scaling limit, if we scale the number of particles with time, we're going to end up with this result where the position of the leftmost particle, nu1, where I've written this as a function of time, the difference between this and the expected particle bulk position, if we scale this with time of the order t to the 1/3, the probability that this whole thing here is going to be greater than alpha is going to be the Tracy-Widom distribution of alpha. So in effect, what we're doing is we're measuring how far away this particle is from the expected mean position. And we're taking the fluctuations, which we're expecting to be of the order t to the 1/3. And if we, in the long-term limit, if we take this, we end up basically with something around a constant, which gives you the Tracy-Widom distribution. So this is going to show you that the TARCEP in this sense has fluctuation exponent of t of 1/3 in time. So this says that we're going to be within the KPZ universality class. And I haven't shown the details, but all this can be made 100% rigorous. I guess this is probably a good point to stop for questions before I move on. If anyone has any. Okay, I guess I can move on. Now I guess I'll get to the meaty part of the talk, which is about the two-species model. So we're going to consider a two-species analog of this TARCEP, which I'll call the 2-TARCEP. And this is going to evolve with these rules. So we're going to have type 1 particles being able to move to the right at rate 1. The same goes for type 2 particles. But we're going to have this asymmetry here where these type 2 particles can overtake these type 1 particles, but it can't happen the other way around. So I've shown this on the diagram here where these type 1 particles can move to the right. The type 2 particles can also move to the right, but only the type 2 particles can overtake the type 1 particles. Yeah, so we're going to consider a fixed number of particles. We're going to consider n particles in total. So this includes type 1 particles and type 2 particles. But we're going to require that there's m type 2 particles, which is going to leave us with n minus m type 1 particles. So we're going to be obviously talking about constant number of particles. And then we're going to index these type 2 particles with this list P. So if the index J is in this list P, then that's going to tell us that the jth particle is a type 2 particle rather than a type 1. So in the same way as what we did with the single species model, we're going to consider the 2-TARCEP on Z. We're going to say that the probability of finding the two-task set with positions nu, which is the positions of all particles, with index list p, the rate of change of this probability is going to be given by this master equation. So this master equation looks identical to the master equation of the task set, and it is identical in this form, but the difference comes in when we apply the boundary conditions. So we're going to, instead of just having one type of boundary condition, we're again going to have n-1 boundary conditions, but they can be of 3 different types. And that different type is going to depend on what the order of the particles are at a given time. So here's an example of one of the boundary conditions. You don't need to take too much notice of it, I guess just be aware that it does exist. But I'll rather just give an example of how we deal with these boundary conditions in general. So if we're looking to, if we have 2 particles where one of them is of type 2, if we're looking at a situation here where they're adjacent, but the type 2 particle is to the right and ahead of it, if we enforce this boundary condition on this master equation for the two particles, this is going to give us the expected behavior. So we're going to have that we can evolve into this state by the type 1 particle jumping from this vacant site, or we can have it that the type 2 particle has just evolved from the type 1. So the 2 particles have already swapped. And the only way to evolve out of this state is for the type 2 particle to evolve, to jump over here to the right, which is this green term. Yeah. So this boundary condition is enforcing that we can't, that type 1 particles can't overtake type 2 particles. So here's probably the first new significant result. This looks pretty gruesome at first glance, but we will break it down a bit. So this is going to be the Green's function for the 2 task sets. So this is going to be the analogous result that Tracy and Whittam had for the single species model. So we're going to consider the time evolution on the infinite lattice Z, where we're now going to have the initial positions of all particles mu evolving to mu, and then we're going to have an initial index list P0 evolving to P. And this is going to be given by this multi-integral expression, where again, we've got these integrals here in these Z variables, and we've got n of them. We've got, again, this sum here over the permutations of length n. And then additionally, now we've got another set of complex integrals here in these du variables. These contours are going to surround singularities at these points z. But now we've also got this extra level of, got this extra sum here over a smaller symmetric group, Sm. So this Green's function, we've shown that this is going to obey the master equation. It's going to obey the 3 boundary conditions earlier. And because it's a Green's function, we're going to again expect that there's a delta function initial condition, which is exactly what we've got. So let's break this down a little bit. So here is the formula we had earlier. If I highlight this red section here, what we're going to notice is that this is going to be exactly the task set Green's function that Tracy and Whittam had. So in a sense, we've built this formula from the results that were already known. And then again, we've inserted this extra level beta ansatz here, which is I guess a beta ansatz over the particle orders. And this last line here is just going to be a normalization constant. So this is the traditional approach, which I alluded to at the start, which is going to be we're going to call a nested coordinate beta ansatz. So yeah, that's, I guess, probably the traditional, probably the more obvious way to look at this problem. Anyway, are there any questions before I move on? Nope. Okay. So we're going to want to study some total crossing events here. So this is an example of a total crossing event, just like we did, just like we studied for the for the single species model, except now I'm going to have these type 2 particles here. We're going to dictate that they're all going to start to the left of all the type 1 particles, and then they're all going to overtake all of these type 1 particles. So the type 2 particles end up being overtaking every single type 1 particle. Yeah, and I think the thing to note here is that these events are quite rare, because all these hops occur with exponential, because it's a Poisson process, all these hops occur on exponential clocks. So the probability of having these events is going to suppress exponentially. So these really are rare events. But we're going to require to specify this, that the initial condition, that the initial order of the particles, we set we set P naught so that all the type 2 particles are initially to the left, and we set P so that all the type 2 particles are over to the right. So just a bit of a note here on how we can simplify the evaluation of this function. If we recall this earlier from the Green's function, we had this factor here, which if we're integrating in our u variables around singularities at z, we're going to have a bunch of singularities at each z for ui, for each u. So rather than doing that, if we're considering total crossing events, it just so happens that for each u integral, for each u integration we do, we only need to consider one of these singularities. Only one of them ends up mattering, and that's going to be the singularity at ui equals zi. And you'll notice here that this is a simple pole. So if we want to evaluate this function, this is going to really reduce the complexity if we wanted to evaluate this explicitly. Because now we only need to calculate the residue of a simple pole, which is obviously quite straightforward. So now I'm going to come to another significant result, which says that for total crossing events, the Green's function is going to reduce to something like this, where now I've still got these integrals here in z. I've replaced some of these z's as w's, but I don't have my u integrals anymore. So I've used that previous lemma to simplify the process of integrating out the u variables. And I think the thing to note here, which is really quite interesting, is that these z integrals here, we essentially have the particle behavior in this determinant here of the type 2 particles, type 2 particle bulk. So that's going to be our determinant here over the z's. And then here we've also got this determinant here, which is going to have the w integration variables. And this is going to describe the type 1 particle bulk behavior. So in a sense, for total crossing events, we find that the type 1 and type 2 particle behavior is in a sense separable. And just a bit of a remark here that we could arrive at this result, everything up to now in this talk, we could have arrived at this result by considering a higher rank analog of the stochastic vertex model. And then we can relate this to a rainbow RCEP where where we have n particles, and then we require that each of the particles is of a different species. So this would be an n species RCEP where each particle is represented by a different species. And then we can perform some partial symmetrization. And this ends up relating to the 2 RCEP. So this is probably a more general way to approach this, and we can arrive at this result from here. This, anyway, I'll talk more about this later, but just a bit of a remark that that's what we can do. And this is the other approach, the less obvious approach, which I was alluding to at the start of the talk. And it's also worth noting here that this result is going to depend on our initial and our final particle positions. So we've still got the mu's and the nu's in these determinants. So this result's probably quite significant, and I think it does deserve a proof. So the total crossing events, you recall from the Green's function that we had this factor here. This is the factor which I discussed a few slides ago, but we've also got this extra factor here upstairs. So really we're going to want to try and evaluate these simple poles at ui equals zi but we have to consider that sometimes, depending on what, remember this pi is a permutation of n variables, that sometimes this pi may cancel out, sometimes this factor upstairs may cancel out this factor, and then our singularity is going to be removable. So we've got to really only consider permutations pi which don't interfere. So we're going to actually, for this, if you sit down and you draw enough permutations, we're going to require that pi j is greater than m. Also, if you consider the only permutations pi which satisfy this, we're going to require then, oh, this is going to reduce to, in a sense, the product of two smaller symmetric groups. So we can essentially write this sum that we had over the n, or the permutations of n indices, which has n factorial terms, and we can reduce the complexity by noticing that with this factor, this is going to reduce to the product of the sum of two smaller symmetric groups. So with this, we can then note that Green's function is going to end up being the, I guess, the product of the sum over two smaller symmetric groups, and then we can write these in terms of determinants. So I guess this is a bit of an example of one of the proofs that we tend to do with these formulas. Yeah, where we just sort of notice this nice property, which looks like a bit of a problem initially, but yeah, ends up with this nice result. The other thing to note is because we've got two determinants, the two determinants haven't come from the initial two sums over the symmetric groups. One of the sums over the symmetric groups has disappeared when we integrate it out, and then the other symmetric group sum ends up factoring into two smaller sums. So now we're going to want to now we're going to consider this further. I'm going to define this Pcross, which is different from the Pcross for the single species model. Where now it's going to look a little bit familiar, but I'm going to introduce two walls now, S1 and S2, and they're going to be located at some lattice sites Z as well. And I can define this Pcross here for some initial conditions mu, which I haven't specified yet. And this is going to be, I'm only going to count configurations where all type 1 particles are in between the walls, S1 and S2, and all type 2 particles have gone beyond S2. And I can calculate this by considering the Green's function that I had in the previous example with the product of the determinants and summing over only final configurations which satisfy this condition. To deal with the initial conditions, I'm going to specify that all type 1 particles are going to lie adjacent with each other. So that's going to be the step initial condition. And that's going to be on the non-negative integers. And then I'm going to randomly distribute the type 2 particles, and I'm going to Bernoulli distribute them with a density rho. And this is going to happen on the negative integers. And then if I take the limit of rho to 1, then I'm just going to recover the step initial condition. But we can do this a little bit more generally than the step initial condition. So that was a lot of words. So what does this actually look like? So I'm going to put all my type 1 particles on adjacent positions with the step initial condition. And then I'm going to Bernoulli distribute m of these type 2 particles with density rho. And then if I look at the expected time behavior, we're going to look at total crossing events. So we're going to want to only consider the rare events where these type 2 particles do all overtake these type 1 particles. So here's a bit of a toy example of what this might look like on a space-time diagram. And then I'm going to put my walls in, and I'm only going to count configurations where the type 1 particles lie in between these two walls, and the type 2 particles all end up beyond S2. So these are the only configurations I'm going to consider. So the probability, so to calculate this, I'm going to need the probability of having my initial conditions. And if you stare at it long enough, you can figure out that this is what the probability is going to be. And it's only going to depend on how far along I put my leftmost particle initially. So that's mu1. And then again, you're probably sick of seeing this Pcross notation, but I'm going to define this Bernoulli Pcross with the walls S1 and S2. And I can calculate this by considering well, what's the crossing probability given mu with the probability of having mu? So in a sense, with this Pcross, we've summed over our final positions. And we also need to sum over our initial conditions. And this is going to lead us to this result, which I think is probably the last significant result that I'm going to talk about, where I can evaluate this. And this evaluates in a quite straightforward way using some nested geometric series identities. But essentially what we've got is we've started with that product of determinant formulas. We sum over our initial and final conditions, and we end up with this expression. And this does look a little bit ghastly, but it is quite nice. So we obviously don't have the mu's and u's in this formula anymore. The type 2 particle behavior was given by the determinant of the z variables. This is now given by this, I guess, product of Vandermonde style determinants here. But unfortunately, we still have this integral here over the w's. The rest of it is quite standard, but oh yes, we've also changed the integration variables and inverted them. But I think this is of significance because this is the formula from which we could perform asymptotic analysis. And we haven't done it yet, but I think that's sort of the next step in this project and what we're going to be working on. But yeah, from here, we could potentially perform some analogous style of asymptotic analysis, some steepest descent analysis, to arrive at some limiting behavior results for this two species task set. Yes. Now I'll just sort of talk about a nice simplification of this. So if I guess because we had two walls and I only want to consider configurations where all my particles are beyond this wall S1. I didn't really specify where I could place S1 and S2. So what if I consider S1 being less than minus M? Well, I guess the best case scenario for having some sort of interaction here with this wall would be if our particles are initially adjacent, and then we require that all the particle crossings and the different species interactions happens immediately. And in this condition, in this case, the furthest left that a type 1 particle can be is at position minus M. So if I take S1 to be less than minus M, then this wall is no longer going to have an impact on our calculations. So this is sort of, again, a space-time diagram of what we're going to expect under these conditions. And under these conditions, we end up with this really quite nice formula, which says that this Bernoulli crossing probability with these walls, where S1 is less than minus M, the n minus m integrals I had in the w's, this ends up collapsing into a single complex contour integral over w. Right, so now there's only one w variable as opposed to, well, a lot of them before, depending on the values of n and m. The other thing to note under these conditions is that if we apply the Cauchy-Binet identity, or some people might know it as the Andreeff identity, then we're going to end up with these z, with the nested integral of the z's is going to be the determinant of a single z integral. The matrix entry from which we calculate the determinant is going to be given by I and j, and I and j are just going to be the power. The only place they appear is as the power here, so as the power of the z here. So really, this isn't going to affect, the matrix entry isn't going to differ too drastically. So this really is a dramatic simplification for what we had earlier. But of course, this is only under the condition S1 minus M. And yeah, that's just a nice little simplification, which I thought I'd include. So I guess now I've got the outlook of where we're going to take this in the future. So if we recall the TARCEP limiting behavior of Gier-Hansen, which showed that this TARCEP was lying within the KPZ universality class, we'd want to sort of look at this two TARCEP model in the same light and see what we can arrive at. There has been a little bit of progress on this recently, where the case of one type 1 particle, so that would be the case in our notation, we would specify that n is equal to m plus 1. This shows that we get, this shows rigorous results for the limiting behavior in this case. Now, we haven't run through what we would expect exactly from our results, but I guess a naive sort of look at our results and it seems to show that what we would get would probably agree with this recent result. But yeah, again, I guess the hope is that, well, with what we've done here, that maybe we could generalize this. And of course, another obvious generalization of this would be to consider, again, the higher rank stochastic six-vertex model. And then if we were to perform a different partial symmetrization to what I alluded to earlier, we could come up with integral expressions for an n species tar set. And then potentially from there, we could come up with like an analogous total crossing events for these n species tar sets. And we'd want to look at if these formulas had the same sort of elegant simplifications, and then maybe even eventually the same sort of limiting behavior. But yeah, that's all for the future. Anyway, I think that's all from me. Here's some references, and thanks for listening in.
All right, let us thank